This is an introduction to the material on chemical equilibria that's in Chapter 6 of your Quantitative Chemical Analysis textbook. When we talk about chemical equilibria, we're talking about a balanced chemical equation for a reaction that can go in a forward and reverse direction. So the reactants can form products. Those products can be converted back into reactants. Each of those forward and reverse reactions in the equilibrium expression has a rate constant, K forward, K reverse, shown here as lowercase k's. The equilibrium constant is shown as a capital K, and this is defined as the concentrations of the products over the concentrations of the reactants, with everything raised to their individual stoichiometric coefficients. This is a unitless quantity by definition. Even if the units don't appear to work out, we define K as being unitless, and it's constant at a given temperature for a given reaction. What can we do with it? At the very basic level, we can determine whether the forward or the reverse reaction is favored. The magnitude of K can tell us the extent of the reaction. By how much is the forward or reverse reaction favored? If we perturb the system, move it out of equilibrium, we can figure out which way it's going to go back. Or if we come upon a reaction at a given place, we can tell whether it needs to make more products or makes more reactants to reach equilibrium. And something we're not going to do in Chem 300 is that if we know K for one reaction, we can determine the K for a related reaction. Finding the equilibrium constant experimentally, there's a few ways to do it. First of all, we can just mix the two reactants, wait for equilibrium to be established, and then measure the concentration of everything and use the equation. We can also measure the forward and reverse rate constants if we can make that measurement, because another expression for the equilibrium constant is that it is the ratio of the forward to the reverse reactions. We can also use thermodynamics. Depending on the thermodynamics of the reaction, we can use a different equation that we'll talk about in lecture to calculate K. The equilibrium constant K is a specific example of a quantity called the reaction quotient, which is defined the same way. The difference between a reaction quotient and an equilibrium constant is that the reaction quotient applies at all reaction compositions, whereas the equilibrium constant is the specific case for when the reaction is at equilibrium, and in this case we give the quotient a new name, K. We can compare Q and K to figure out, for any state that the reaction is in, which direction is it going to go to reach equilibrium or to reestablish equilibrium. And this relationship between Q and K is the real way to think about the Chatelier's principle, which a lot of people in sort of the general understanding will recognize as a system being perturbed from its equilibrium proceeds back in a direction that compensates for that change. The reason for this is that at equilibrium the reaction quotient is equal to K, and when you perturb it from equilibrium the reaction quotient changes, and the reaction quotient will the reaction will accommodate for that change such to make Q equal to K again. So for a reaction, any reaction, doesn't matter what it is, we can think about the equation for Q and think about how changing the concentration of any of these products or reactants is going to affect that Q. How is it going to make it bigger or smaller? And therefore, what has to happen for Q to become equal to K again? So you can think about the effect of adding a gaseous reactant, a solid reactant, removing a gaseous product, lowering the pressure, and then adding a catalyst. And you can look at Q and figure out what is each of these changes going to do to Q, and therefore what has to happen for Q to return to the state where it's equal to K. Another thing we can do with the equilibrium constant is to calculate a solubility product, which is the equilibrium constant for the specific kind of reaction where a solid dissolves into ions in solution. At equilibrium, in this case, as much solid has dissolved as is capable of dissolving, and then the dissolution just stops. So for example, calcium carbonate dissolving into its ions. You have calcium carbonate solid as the reactant, and you have two aqueous ions in solution as the product. All the ratios are 1 to 1, the mole ratios. So the solubility product constant for this is just the product of the products, multiply the product concentrations together, raised to their stoichiometric coefficients, which is just 1. In the denominator, we don't have anything. And that's because for any equilibrium constant expression or any reaction quotient, we leave out of the equation solids, pure solvents, and elements that are in their standard state. So for example, hydrogen gas. What can we do with it? Well, we can figure out solubility at the very basic level. We can also predict the results of a precipitation titration, gravimetric analysis, so predict how much of a solid we're going to get, or how much is going to be left over. And then we can do selective precipitation, which is a process of removing interference by precipitation. So we add an ion that we know is going to precipitate with our interferent, but not with our analyte, and we can remove the interferent that way. Factors that affect solubility, these include ionic strength, which we will talk about in Chapter 7, but not for Exam 1, pH, which involves the common ion effect, and complex formation, if any. So we're going to talk about all these things briefly in Chapter 6, in more detail in Chapter 7.